If I give you a perfect microscope, perfect lenses, perfect light, can you finally pin down an electron's position and speed at the same time? Most people's gut answer is yes, of course. If the only problem is that our tools are crude, then better tools should fix it. Sharper lens, brighter light, cleaner detector. That's how the whole history of science feels. You improve the instrument and the fog clears. And then you hear the sentence said with the kind of confidence that makes you suspicious. You can't. Not even in principle. Not even with a magical microscope. There's a limit, a hard limit. And it's not because your hands shake. That's the uncertainty principle. But here's the part that causes endless confusion. People say it like it's a rule about measurement. When you measure the electron's position, you disturb its momentum. That sounds plausible. It even sounds kind of comforting. It means reality is still classical underneath, and we're just clumsy. We're poking the thing, so we mess it up, so we don't know it. Except that story isn't the uncertainty principle. It's related. It's not completely wrong, but it's not the heart of it. And if you build your understanding on that alone, you'll keep running into contradictions. So let's do this like an investigation. We'll put the usual explanation on the stand, let it say its piece, and then we'll bring in 2 other witnesses. By the end, you'll see why uncertainty isn't really about ignorance. It's about what kinds of states the universe allows you to prepare. Start with what you already believe, because it's reasonable. In everyday life, objects have a position and a velocity. A baseball is here, moving that way. Even if you don't know those numbers, you think they exist. If you had a better camera, you could know them better. So you carry that idea into atoms. An electron is like a tiny baseball, and if saw pumps, he had tiny cameras, we could track it. Now the title of this video is basically picking a fight with that belief. No one explains it like this. Means we're not going to just repeat the slogan. We're going to ask very carefully what we mean by know, what we mean by position, what we mean by momentum, and what experiments force us to change the picture. Let's give the measurement disturbance story its best possible version first, because it's not random. It comes from a real and clever thought experiment that Heisenberg himself discussed. Imagine you want to see an electron. You can't just shine ordinary light and take a photo the way you do with a person, because light has a wavelength. If your wavelength is huge compared to what you're trying to see, you can't resolve it. That's why you can't see bacteria with a cheap flashlight. You need shorter wavelength light, like ultraviolet, or even X-rays, to see smaller details. So if you want to locate an electron with high precision, the natural idea is use very short wavelength light, gamma rays, really tiny wavelength. Then your pixel size gets very small, and you can localize the electron more precisely. But the catch is that light comes in packets, photons, and those photons carry momentum. Shorter wavelength photons carry more momentum. So when a photon scatters off an electron and enters your microscope, it gives the electron a kick. The more energetic the photon, the more momentum it can transfer. So the more precisely you try to determine the electron's position, the more you kick it, and the less certain you are about its momentum afterward. That story feels like a trade-off, and it is a real trade-off in many measurement setups. You can learn something, but in learning it, you can change something else. There's even a general concept in physics called back action. The measurement device interacts with the system. There is no pure observation. So what's wrong with using that as the uncertainty principle? Here's the first crack. Suppose the uncertainty principle were only about disturbance from measurement. Then it would be a statement about the act of measuring. It would imply that before measurement, the electron had a perfectly definite position and momentum. You just can't access them without messing one up. But quantum mechanics doesn't treat it that way. Quantum mechanics says that even before you touch it, even if you do nothing, the electron can be in a state where position outcomes are spread out and momentum outcomes are also spread out. And there is a lower bound on how sharp both can be at the same time. That's a statement about the state, not your clumsy hands. You might say, okay, but we only learn the uncertainty by measuring. Isn't it still a measurement issue? Not quite, because you can predict the spread of outcomes from the way you prepare the system. The uncertainty can be there as a feature of the preparation, even if you never actually perform both measurements. Let me make that concrete. Imagine I prepare an electron in a certain way, and then I perform a position measurement on a large number of identically prepared electrons. And I don't measure momentum at all. I just record positions. After many runs, I get a distribution. Sometimes the electron lands here, sometimes there. That distribution has a width. Now I do a different experiment. I prepare the same kind of state, but instead of measuring position, I measure momentum on a large number of runs. I get a distribution of momenta. That also has a width. Those widths are not about my microscope being imprecise. They are about the fact that the state does not predict a single outcome. It predicts a range with certain probabilities. And the uncertainty principle is about how narrow those two distributions can be simultaneously for the same prepared state. That's already a different flavor than you disturbed it when you measured. It's about what the state contains, what it allows. So why do people keep telling the microscope story? Because it's a bridge from classical thinking. It's a way to make the trade-off feel physical. But if you stop there, you'll keep thinking uncertainty is just a kind of technical difficulty. Let's bring in the second witness, waves. Now watch what happens when you know where it is by forcing it through a narrow opening. The outgoing directions spread, even if you never look at it afterward. This is one of the most satisfying demonstrations in all of physics because you can do it with light, with water waves, with sound, with anything that behaves like a wave. It's not even quantum yet, it's just waves. Take a beam of light and send it through a narrow slit. On the other side of the slit, the beam doesn't continue as a perfectly straight narrow line. It spreads out. It diffracts. If you put a screen far away, you'll see a pattern, a bright central region and dimmer fringes, depending on the slit shape. And here's the key observation. The narrower the slit, the wider the spreading angle. The more you confine the wave in position at the slit, the less confined it is in direction afterward. That's not because your measuring device disturbed the light. No one measured anything. It's just the way waves propagate. If you want a vivid everyday anchor, imagine spray painting through a stencil. If the stencil has a big opening, the paint can travel through mostly straight, and the sprayed region on the wall stays relatively focused. But if the opening is tiny, the paint jets out in more directions. You get a broader fan. Narrow the opening, and the spread increases. With light, the spreading isn't because paint molecules bounce randomly. It's because the wave that passes through a small aperture can't remain a single, clean direction. It becomes a superposition of many directions. Now take that idea and connect it to momentum. For a particle, momentum points in a direction. If a particle is moving mostly straight, its momentum is mostly straight. If the particle can emerge in a wide range of directions, its momentum has a wide range of transverse components. That is, the momentum sideways is uncertain. So the slit experiment says, if you localize something in space to within a small region at the slit, you necessarily produce a spread of momentum directions afterward. And again, this is not about your camera. This is about the wave-like nature of what's passing through. At this point, a reasonable person asks, so are you telling me the uncertainty principle is just diffraction? Almost, but not quite. Diffraction is a classical wave phenomenon. The uncertainty principle is a quantum statement about the relationship between the distributions of outcomes for certain pairs of measurements. The bridge between them is that quantum particles are described by wave-like amplitudes. The same math that makes light diffract shows up when you describe electrons as waves. But to really see the deep reason, we need the third witness, the structure of waves in general, not just the slit. The fact that any wave packet has a built-in trade-off between how localized it is and how definite its wavelength is. Here's the twist. The uncertainty principle is already hiding inside ordinary waves, long before you say the word quantum. Think about a pure musical tone like a tuning fork. If it vibrates steadily, it produces a single frequency. In a graph of the air pressure oscillation, you'd see a nice sinusoid that goes on and on. That wave is extremely definite in frequency. It's basically one pitch. But where is that wave located in time? It's not localized. It's spread out across time. It's just there, forever. Of course, in real life, it doesn't last forever, but the more you want a sharply defined frequency, the longer you have to let the wave exist. Now flip it. If you make a short, sharp click, a snap of your fingers, that sound is very localized in time, but it doesn't have a single pitch. It contains a wide range of frequencies. It's noisy and broadband. This is not a mysterious quantum rule. It's just a mathematical fact about waves and how you build them from sinusoids. A highly localized wave packet is made of many different wavelengths. A single wavelength wave extends indefinitely. If you've ever seen a barcode scanner, there's an odd parallel. A perfectly sharp spatial feature, like an abrupt transition, requires many different stripe spacings in the underlying pattern. If you limit yourself to one stripe spacing, you can't make a sharp edge. You get a smooth wave. Sharpness demands a mixture. That mixture is the core idea. Localization in one domain requires broadness in the conjugate domain. Time frequency is one example. Space wave number is another. Now do space wave number, because that's the one that becomes position momentum. Imagine a wave on a string. A pure sinusoidal wave has a well-defined wavelength. If the wavelength is well-defined, the wave is spread out over the entire string. There is no where it is, it's everywhere. If you want a wave packet, a bump, traveling along the string, you can make one, but you have to add multiple wavelengths together. When you superpose waves with slightly different wavelengths, you can create a localized envelope. The narrower you want the envelope, the wider the range of wavelengths you need. That relationship is exactly the Fourier transform. If you don't care about the name, the idea is simple. Any complicated shape can be built from many sinusoids. And the sharper the shape, the more variety of sinusoids you need. In physics language, the variety of wavelengths corresponds to a spread in wave number, usually called k. And for quantum particles, momentum is proportional to wave number, p equals h times k. That's de Broglie's relation in a modern form. So if a particle's wave function is localized in space, narrow dx, then it must be built from a wide range of k values, large dk, and therefore a wide range of momenta, large dp. That's the uncertainty principle in its most inevitable form. It's not that someone decreed a limit, it's that if a particle is described by a wave-like amplitude in space and momentum corresponds to its wave number content, then there is an unavoidable trade-off between spatial width and momentum width. At this point, the principle feels less like a philosophical statement and more like a geometry constraint, like trying to draw a rectangle with a fixed area. If one side shrinks, the other must grow, not because of your tool, but because of the shape you're drawing. But let's not oversell it. There's still a subtlety. The Fourier relationship between position and momentum wave functions is true in quantum mechanics, but why does quantum mechanics insist on describing particles with wave functions at all? Why not just keep classical particles and blame disturbance? This is where Feynman's perspective is so powerful, because he doesn't start with a mystical statement. He starts with experiments that force you to abandon the classical picture. Feynman's move is brutally simple. Stop asking what the electron really did and ask what pattern your setup can predict. Take the famous two-slit experiment. Fire bullets at a wall with two holes, and beyond the holes, a detector screen. Bullets are classical. Each bullet goes through one hole or the other. If you close one hole, you get a single lobe distribution on the screen. If you open both holes, you get the sum of the two distributions. That's exactly what you expect. The probability of landing at a point is the probability via hole A plus the probability via hole B. Now do the same thing with waves, like water waves or light waves. With one hole open, you get a diffraction pattern. With both holes open, you don't get the sum of the intensities. You get interference. There are regions where the waves add and regions where they cancel. So the pattern is alternating bright and dark bands. Now do it with electrons, one at a time. You might expect bullets. But what you see is that after many electrons, the pattern builds into the interference pattern. Electrons individually arrive as localized hits, clicks, but collectively the distribution shows interference, as if a wave passed through both slits. This is the only mystery, as Feynman liked to emphasize. How can you have something that arrives as a single localized event, but produces a pattern that requires wave-like interference? The minimal consistent explanation is that you don't ask. In a classical path, you assign an amplitude, a complex number. For each possible way the electron can get to a point, there is an amplitude. The probability of detection is the square of the magnitude of the total amplitude, where the total amplitude is the sum of contributions. Because amplitudes can add or cancel, you get interference. Now, what happens if you try to find out which slit the electron went through? If you set up any apparatus that can reliably tell you which slit the electron used, the interference pattern disappears. The distribution becomes the sum of two single-slit distributions, like bullets. Why? There are different ways to say it, but here's the key point for uncertainty. The setup that gives you which path information necessarily changes the quantum state in a way that destroys the phase relationship between the two paths. The state no longer supports interference. Notice what we did here. We didn't say you disturbed it. We said the physical situation no longer allows the coherent superposition of alternatives that produces interference, and that's a statement about the state and what it predicts. Now connect this back to uncertainty. In the two-slit experiment, if the slits are separated by some distance, then having which path information means you have localized the electron to one slit or the other. That is a kind of position information, not a continuous x value, but enough localization to say left region or right region. And it turns out that if you enforce that kind of localization, you necessarily create a spread in transverse momentum that washes out the interference fringes on the screen. You can think of it like this. Interference fringes require a delicate pattern of phases that correspond to different transverse momenta. If your state becomes too definite about position at the slits, it becomes too broad in transverse momentum, and the fringes get blurred. The wave packet's momentum content gets spread. This is exactly the same story as the single-slit diffraction, now placed inside a quantum experiment where the only consistent way to talk is in terms of amplitudes and probabilities. So now we have the picture. Uncertainty is built into wave-like descriptions, and the wave-like description is forced on us by interference experiments. That's why it isn't optional. But I want to pause and ask a very specific question because it's the question people usually avoid. What exactly do we mean by uncertainty in the uncertainty principle? We don't mean that the electron is hazy, like a smudged dot in reality. We mean that if you prepare a system in a given state and you measure position many times on identically prepared systems, you will get a distribution of outcomes. That distribution has a width, which we can quantify as a standard deviation. That standard deviation is dx. Similarly, if you measure momentum many times on identically prepared systems prepared the same way, you get a distribution of momentum outcomes. That distribution has a width. Those widths are not errors. These terms are not about your instrument being sloppy. They're the spread that the state predicts. That's a huge psychological shift. In classical physics, a distribution usually means you don't know the underlying definite value. In quantum physics, the distribution can be the whole story. The state does not contain a single sharp value for both observables simultaneously. If you're thinking, that sounds like giving up, it is a kind of giving up on the idea that physics must always describe hidden definite values. But it's not giving up on prediction. Quantum mechanics is incredibly precise about predicting the distributions. Now, if you want the most compact, no-nonsense formulation of the uncertainty principle, it comes from the algebra of the theory. If you want the shortest honest definition, it's this. Position and momentum are not just two numbers. Quantum theory represents them with operations that don't commute. Here's what that means without getting buried in symbols. In classical physics, if you have a state of a particle, you can think of position x and momentum p as two properties you can list simultaneously. There is a point in phase space. If you do things in different orders, measure x, then p, or p, then x, you are assuming those operations refer to properties that can be jointly assigned. In quantum mechanics, the operations corresponding to measuring x and p do not behave like that. The mathematical objects we use, operators, do not commute. Doing one then the other is not equivalent to doing them in the opposite order at the level of how they act on a state. The commutator, the difference between xp and px, is not zero. It's proportional to h, Planck's constant over 2p. That single non-zero commutator has consequences. One of them is an inequality. The product of the standard deviations of outcomes for x and p in a given state must be at least h2. It's not a technological limit. It's not a conspiracy. It's a theorem. If your theory uses that non-commuting structure, which it must, if it is to match experiments like interference, then it follows. Now you might be thinking, but you just pulled operators out of nowhere. Isn't that an appeal to math authority? It would be if I said, trust the operators, but we don't have to do that. We can instead see the operators as the formal encoding of the wave-Fourier relationship we already discussed. The reason position and momentum are Fourier pairs in quantum mechanics is that a momentum state looks like a plane wave in position space. A definite momentum corresponds to a single wavelength wave function extending through space. A localized position state requires a superposition of many plane waves, many momenta. That's the same Fourier story, but now the wavelength content is literally the momentum content. So the algebra isn't an arbitrary choice. It's the compressed version of the wave behavior. It's the way the theory keeps the bookkeeping consistent. Now we're ready for the synthesis, and this is where I want to cash in the promise of the title. So, though, the uncertainty principle isn't saying measurements are hard, it's saying the world only offers certain kinds of states, and those states can't be sharp in both conjugate directions at once. Let me say it with an image in your head. Imagine you're trying to design a stamp that prints a very sharp dot on paper. If you carve a perfect tiny dot, you might think you'll get a dot, but the ink spreads, or the paper fibers blur it. That would be a measurement instrument story. Now imagine a deeper problem. The ink itself can only flow in certain patterns. No matter how perfect your stamp is, the physics of ink flow prevents a dot narrower than some width without creating splatter. The splatter isn't a defect of your stamp. It's a consequence of the medium. Quantum uncertainty is like that. The medium is the wave structure of quantum states. When you localize the wave function in position, you necessarily create a superposition of many momenta. That means that if you later measure momentum, you don't get a single value, you get a spread. And the product of those spreads has a lower bound because of the Fourier mathematics and the non-commuting structure. Where does measurement disturbance fit in this picture? Measurement disturbance is one way to produce the trade-off in practice. If you try to measure position sharply, the interaction between your probe and the particle will typically change the particle's momentum distribution. That's real. But that's not the foundational reason the trade-off exists. Even if you somehow prepare a state with a narrow position distribution without kicking it, say by letting it pass through a slit without observing, it will still have a broad momentum distribution afterward. The spread is there in the state. So here's the clean map. 1. Uncertainty is a property of a prepared quantum state. It describes spreads of outcomes across many runs. 2. Those spreads are constrained because position and momentum wave functions are Fourier related. Narrow in one means broad in the other. 3. The deeper algebraic reason is non-commutation, which encodes that same structure and gives you the precise inequality. Once you have that map, a lot of confusions dissolve. For example, people ask, is the electron really in many places? The honest answer is, the wave function assigns amplitudes across space, and the outcomes of position measurements are distributed accordingly. Whether you want to say really in many places is a matter of interpretation, but the statistical predictions are unambiguous. The uncertainty principle is about those predictions, not about our language. People also ask, can we beat it with better technology? You can reduce measurement error. You can make detectors more precise. But the uncertainty principle is not measurement error. It's about the intrinsic spread in outcomes for a given state. You can prepare different states, squeezed states, for example, redistribute uncertainty between conjugate variables. But you can't make the product arbitrarily small for the same pair. The limit stays. Another common question is, so does thou, is mean nature is random? Quantum mechanics predicts probabilities. In that sense, it contains irreducible statistical behavior. But that's not the same as saying anything can happen. The distributions are highly structured. They follow precise rules. The uncertainty principle is one of those rules. Now, since we promised a like this explanation, I want to give you one more angle that many explanations skip. Why the uncertainty principle is not a weird add-on, but a necessary ingredient for consistency, and why it actually makes the universe stable. Imagine a world where an electron in an atom could have both a perfectly definite position and a perfectly definite momentum, like a little planet in orbit. Classical intuition says it would orbit the nucleus like a tiny solar system. But classical electromagnetism says that an accelerating charge radiates energy, An orbiting electron accelerates constantly, so it would radiate, lose energy, spiral inward, and crash into the nucleus. Atoms would collapse. Matter would be unstable. In the real world, atoms are stable. Electrons don't just crash, they occupy stationary quantum states. And one reason you can't cram an electron into an arbitrarily small region around the nucleus is precisely because confining it increases its momentum spread, which increases kinetic energy. There's a balance. That's not a full derivation of atomic structure, but it gives you the flavor. Uncertainty is not just a limitation, it's a structural feature that prevents classical catastrophes. It's part of why chemistry exists. So once you see uncertainty as a shape constraint on possibilities, you stop fighting it and you start using it. Physicists use uncertainty as a design principle. If you know you've localized something tightly, you expect momentum spread. If you want a narrow energy line, you expect a long-lived state. If you squeeze uncertainty in one quadrature of light, you expect it to swell in the other. The principle becomes a tool, and that's the final shift I want you to walk away with. The uncertainty principle isn't the universe hiding information from you like a prank. It's the universe telling you what kinds of questions can have sharp answers at the same time, given the way quantum states are built. If you go back to the opening question, perfect microscope, perfect light, what's the answer now? The answer is no microscope can beat the fact that a state sharply localized in position must be a superposition of many momenta. Even if your microscope didn't disturb the particle at all, the very condition of being localized is incompatible with having a narrow momentum distribution. The limit lives in the state, not your hands. And that's why when people say no one explains it like this, what they really mean is stop thinking of uncertainty as ignorance. Start thinking of it as geometry, as the unavoidable trade-off between two ways of describing the same wave-like reality. The weirdness doesn't go away, but it becomes a clean weirdness, a kind you can reason about. And once you can reason about it, you're not lost in the fog anymore. You're standing on solid ground, looking at a universe that's stranger than classical intuition, but also more coherent than any half explanation ever made it seem.